The immense Sahara Desert is the second largest in the world. Originating in deserts, it is common that yellow clouds of sand are whisked up and carried all over the world. Prevailing northerly winds carry the sand clouds thousands of miles, sometimes reaching over the Alps and falling on countries in northern Europe. Sand from far-off places has a decisive influence on our weather and can alter long-term climates all over the world. Warm desert air currents and wind sweep the sandy dust up into the atmosphere. The sand forms gigantic dust carpets, some the size of Spain. Drifting off the west coast of Africa, some sandstorms journey across the Atlantic Ocean towards the Caribbean and Brazil. Some of the sand ends up falling on the Amazon rainforest. Surprisingly, the sand provides the flora with a valuable nutrient-rich shower. The sand contains minerals vital to the forest's ecosystem, such as calcium, phosphorus, and potassium. Since the forest floor does not provide many of these elements, many mosses and different types of orchids have evolved rootless, growing high in the trees. They extract nutrients from the air around them. The Saharan sands that travel the world help the forest survive through this regular fertilization. However, traveling sands are not always helpful. A regular sandstorm that begins in spring in the deserts of Mongolia often pesters the residents of Beijing. Sometimes over 300,000 tons of sand rains down. The problem seems to be getting worse, and large portions of the countryside are succumbing to the desert sands. Intense farming methods and clear felling of trees for industrialization have contributed to the decline. China loses about 2,500 square kilometers every year to desertification. China is not the only country facing the problems of desertification. Strong winds that whip up sand and dust particles have been intensifying all over the world. More sand is finding its way into the atmosphere than ever before. Researchers fear that the production of dust from the world's arid regions has increased 33%. Water molecules attach themselves to this mineral dust, aiding cloud formation. Over the past few decades, the incidence and strength of hurricanes has increased. The number of Category 4 and Category 5 strength storms has nearly doubled. Often forming in the Atlantic Ocean, the Caribbean, and the Gulf of Mexico, the United States gets the brunt of many of these weather events. Could there be a relationship between the dust storms and hurricanes? Atmospheric researchers have concluded that between 1/3 and 1/2 of the dust transported from the Sahara moves on a trade wind jet stream towards Florida. The researchers are looking for a link between the sand content in the atmosphere and the area of the atmosphere where the probability is most favorable in regard to hurricane development. The Falcon is a research aircraft that flies into Morocco to study the Sahara Desert. Atmospheric researchers, geologists, and mineralogists test all of the equipment before their flight to ensure that everything goes smoothly. In addition to the specialized equipment on board, there are lasers mounted on both wings and on the fuselage. The Falcon's specialty is its ability to conduct research in the troposphere at an altitude of over 12 kilometers. The scientists will attempt to measure the exact mass, height, and width of a sand stream. One of the research facilities is established in an oasis town at the southern foot of the Atlas Mountains in Morocco, located at the edge of the expansive Sahara Desert. The research team uses LiDAR lasers that work on a simple principle. They measure particles using reflected light. Every 30 milliseconds, the laser fires short impulses in duration of 10 nanoseconds. As it is fired into the atmosphere, it comes in contact with sand particles. The light is then reflected back to a large telescope. A decoder measures the amount of light returning. If the light returning is high, there are a great deal of particles in the air. The fewer the particles present, the less light that will be reflected back. The distance of each particle is calculated depending on the amount of time it takes for the light to return. The scientists are evaluating a large segment of airspace between the altitudes of 400 meters and 60 kilometers above the desert. They must work quickly because summer is coming and the lasers will not work as well in an environment with scorching temperatures. Next to the hangar that houses the lasers, a team of scientists is preparing an additional airplane. This small turboprop plane is equipped with a photometer that measures how much sunlight passes through sand clouds. The photometer splits the rays of sunlight into their basic components. This will tell them how much sunlight is getting through, how much is being reflected, and how much is trapped in the sand clouds. Meanwhile, the Falcon is preparing to take off on a course set by ground control, following a pattern set by the ground-based laser beams and the latest satellite reports on the dust cloud's movement. The data from the Falcon supplements the measurements taken from the ground. While the ground-based lasers run vertically into the sky, the Falcon's lasers run horizontally into the clouds. The turboprop plane is implementing its mission, flying as low as possible where the other instruments are unable to measure how much sunlight comes through the dust cloud. These three methods of collecting data are ideal solutions for the scientists. Each method complementing the other, all measuring the same event at the same time in hopes of unraveling the secret of the airborne desert. This is Calypso, the Cloud Aerosol LiDAR and Infrared Pathfinder satellite observation platform. It researches the relationship that clouds, atmospheric aerosols, and airborne particles have with Earth's weather, climate, and air quality. Calypso includes an active LiDAR, a passive infrared imaging radiometer, and a visible wide-field camera. Orbiting at a height of 800 kilometers, it uses pinpoint accuracy to plot the course of Saharan sand moving over 5,000 kilometers into the hurricane zone. At the hangar, the team of scientists have a preliminary look at the raw data. It appears that the dust cloud is consistently 5 kilometers thick over the desert, and the top of the cloud is completely flat. The Atlas Mountains have acted as a ramp for the cloud to push up and off over the Atlantic Ocean. The data also implies that the more compact the cloud, the further it can travel. Scientists have determined that the dust particles are relatively large. This raises concern about whether or not the sunlight is penetrating, reflecting, or being absorbed by the dust cloud. At 2 to 3 microns, or 2 to 3 thousandths of a millimeter, they are large compared to other atmospheric particles. As a basis for comparison, this mosquito is 20 millimeters long, and the sand particle on its back is 4 to 5 microns in diameter. At this size, scientists are concerned that the particles are absorbing a lot of energy from the sun. The LiDAR pulses also show that the formation of clouds is greatly increased by the role the particles play. In turn, clouds reflect the sunlight, cooling the desert. They were surprised to find the existence of ice particles in higher altitudes above the cloud formations. There are indications that snow and rain are present, but evaporate before reaching the ground. The sand that is whipped up high into the atmosphere is responsible for the ice formation. The dust particles act as condensation seeds, as tiny water droplets attach themselves, ultimately allowing vapor droplets to form. This is how cooling clouds come into existence. However, they have learned that the dust consists of particles of varying properties, some of which store the sun's energy faster and to a greater extent than others. Another team of experts in the field of environmental mineralogy are in Morocco, to the south near the Algerian border. They're using a complex dust collecting station that filters sand particles from the air and sorts them by their different sizes. Their goal is to build an accurate picture of the minerals present in the sand. They have found the presence of iron-based minerals that absorb the sun's rays and are responsible for the decrease in the amount of light reaching the ground. The results show in some places the atmosphere is warmer and the ground is cooler. To decipher which particles tend to attract water, they are artificially humidified. Researchers observe which ones swell up the most when they come in contact with the water vapor. The particles from the dust collector are sampled on layered copper plates and further analyzed under a microscope. The different minerals vary in color and therefore absorb light from different wavelengths. Darker particles trap more sunlight, while lighter colored particles permit more light to pass through. Scientists are able to produce a more detailed chemical analysis of the particles using an electron microscope. It scans the surface of the particles with a powerful beam of electrons, creating a magnification up to 1/1,000,000th of a millimeter. The team has hundreds of samples to process, all from the Sahara, but early results show that calcium seems to predominate, and gypsum, better known as plaster, and silicates. The measurements taken by the lasers confirm that a high proportion of the sun's rays are being deflected away from the Earth due to the high calcium content of the dust cloud. This means the desert sands far below are being cooled. To find out which particles promote the formation of water vapor clouds, a cooling element is added to the microscope. The vapor turns into ice, thus becoming more visible. Ice seeding research is still in its infancy, but we know that the physical structure of the particle is important. Ice forms more readily on objects with multilateral surfaces. It also forms promptly on silicate-based surfaces, which makes up the majority of the particles in the Saharan desert. The silicate content of a dust cloud moving out over the Atlantic has been measured at between 70 and 80%. This dust is making the deserts cooler and the oceans warmer. More clouds, more rain, and less vaporization is the result of a warming of air masses over the ocean. Relative to their finds and recent history, hurricanes gather their energy from the vertical convection of water vapor. Less vapor means less convection, resulting in a calmer atmosphere. According to this logic, they believe that the dust clouds of the Sahara could actually be interrupting the formation of hurricanes. If you are interested in an exciting and challenging career as an atmospheric scientist, studying physical characteristics, motions, and processes of the atmosphere, and the way in which these factors affect the rest of our environment might be rewarding. Many meteorologists find their career paths leading to the National Oceanic and Atmospheric Administration and the Armed Forces. Other meteorologists and ecology experts conduct research at the university level. With the help of ecologists and atmospheric scientists, it has become evident that even areas like the Saharan Desert, with uninviting and inhospitable conditions, can positively affect and help sustain life over extensive regions at distant parts of the globe.